Okay, hi. So in this video, we will look at the binomial distribution. X is distributed binomial n comma p, but in particular at two distributions that are friends of the binomial distribution. Let's say y is distributed Poisson lambda, and the other friend is z is distributed hyper-geometric. I will just write hype here. And let's parameterize that one with N, R, and capital N. Okay, so in class and in another video, we've dealt already with a binomial distribution. So the probability mass function f of x, that's the probability that p of x equals x for a binomial distribution, is n choose x, p to the power x, 1 minus p to the power n minus x. And that is for x on 0 up to n. Okay, and 0 otherwise. And this binomial distribution, it counts the number of successes in n Bernoulli trials, n independent Bernoulli trials, each with success probability p. That's what you get with your random variable x. Now, we will start by speaking about the Poisson distribution, and then we'll relate the Poisson distribution to the binomial distribution. And similarly, later we'll speak about the hypergeometric distribution and also relate that to the binomial distribution. Okay. So y is distributed Poisson. I'll just write POI with the parameter lambda. Lambda is a strictly positive number here. If the probability that y equals y is e to the minus lambda, lambda to the power x divided by x factorial, and that is for x equaling 0. Sorry, let me put an x here. Probability that y equals x, and that is for x equaling 0, 1, 2, up to infinity. So all of the non-negative integers. And 0 otherwise. So that is the probability mass function of a Poisson random variable. So before we say something about it, let's just see that it's a probability mass function. So each of these entries are strictly positive for any x, so that's okay. We get that's one criteria. The other one is that the sum of x going 0 to infinity of f of x needs to be 1. So let's look at that sum. Well, before we do anything, let's observe that e to the minus lambda does not depend on x, so that's a normalizing constant, which we can just write that out. So that's e to the minus lambda times the sum x going 0 to infinity of lambda to the power x divided by x factorial. But the thing is that this thing is nothing but the Maclaurin series or the Taylor series around 0 for e to the power lambda. So what we get here is e to the minus lambda as we had before times e to the power lambda, and that's just e to the lambda minus lambda or e to the 0 or 1. So good. So that is a valid probability mass function. Okay. Now it turns out that the parameter lambda is the expectation. So kind of like a normal distribution where you have a parameter for the expectation, but it's also that the parameter lambda is the variance. So a Poisson distribution has this characteristic that the expectation and the variance are the same. Let's just go ahead and carry out that computation. So the expectation of y, that is going to be the summation of x going 0 to infinity of x e to the minus lambda, lambda to the power x divided by x factorial. Okay, so we're summing up over all possible probabilities and multiplying them by the possible value x. Okay, so it's this series. Now, the first term here is, of course, 0, because for x equals 0, the first term is 0. So we might as well write the summation from x going 1 to infinity of e to the minus lambda, lambda to the power x times x here still, divided by x factorial. And observe that this x and the highest multiplicand in x factorial are both x. So we can represent this as a summation x going from 1 to infinity of e to the minus lambda, lambda to the power x divided by x minus 1 factorial. Okay. Now, when we see this type of thing, it kind of makes us want to maybe, well, instead of summing from 1, let's just sum here from 0, because the first term is 0, x minus, well, 0 factorial, 1 factorial, etc. So let's just now do a shift of the summation once again, and then sum x going from 0 to infinity, e to the minus lambda. So now it's lambda. And look, here we need to put x plus 1, right? So if we sum from 0, the first term here is the first power is lambda to the power 1. That's like lambda to the power 1 we had here, right? So we're going to put an x plus 1 in the exponent. And here, x factorial. And now we can see that we can take out this extra lambda from this plus 1. We can take it out of the summation if we would like, and we'll have summation from x0 e to the minus lambda, lambda to the power x divided by x factorial. Now, this was another example. We've already seen one in class. This is an example of what we might call completing to a probability completing the probability distribution, because here we have a summation over all probabilities in the probability mass function. This is a probability mass function of a Poisson, hence it is 1. So the result is that we get a lambda. So that was a derivation of the expectation. You can do a similar derivation for the variance of y. I won't do it all the way. What you need to do is you need to look at the second moment. So the expectation of y squared sum x from 0 to infinity, x squared e to the minus lambda, lambda to the power x divided by x factorial. And the trick you would follow here is up to some point you would get it actually to be in the form of this sum, okay, or perhaps in the form of this sum. So then you'd know that you'd already put it in terms of lambda, right? So from this x squared, one of the x's can make this an x minus 1 factorial, and then you can do a bit more shifting and you'd get the second moment. And then the variance of y is going to be that second moment which you compute minus lambda squared, minus the first moment squared, and you'll see that that's lambda. Okay. So that's all nice and good. But still, how does Poisson distribution arise? Well, I must say that the Poisson distribution is one of the most natural distributions there are. Um, and in a more advanced probability course, you might study something called the Poisson process. So Poisson process is a stochastic process, a process over time that counts events that arrive in a very independent manner. Now, we're not going to be able to speak about Poisson process fully, but what we can speak is we can speak about how a binomial random variable becomes a Poisson random variable when we take n and take it to infinity and take p and take it to 0, but we do this changes between n and p in a very specific manner. So just to motivate this a bit more, think of some time axis between, say, time 0, and let's call this time 1. So you have 1 unit of time, and you're looking at the sky, okay? And you're looking at meteor showers in the sky. So at first, what you decide to do is you decide to just split that time axis of, say, you're looking for 1 minute at the sky, okay, or maybe 1 hour. Maybe if you can look so far for a whole hour at the sky, looking for 1 hour at the sky, and you break it up into n bits. And in each bit, you say, well, do I have a shooting star or not? So do I have a success or not? So the success probability in n bit is going to be p, 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 and the number of shooting stars will indeed be distributed binomial np. That's assuming that, shooting stars, that you don't have some cluster of meteorites that come to you, you just have some random things that are completely independent of the other. It can be a bit of a strong assumption for shooting stars, but can also not be. It depends. Okay, so as a first kind of model, that maybe makes sense. But the only problem is that, there is a possibility that within two time intervals, so let's say if n was 60 and each time interval is a minute, within two time intervals, there is a chance of actually seeing two shooting stars. So what you might do is you might further subdivide your interval by increasing n, let's say from 60 to 120. And in this way, you continue and grow n. You make n bigger and bigger and bigger. But because you've made n bigger and bigger and bigger, in each small time interval, the probability, so what I want to say is n is going to grow, but p is going to go down. Now, if you grow n and suppress p, so you grow n to infinity, so you make many, many, many micro time intervals, and you take p to be 0, so you make this probability to be 0 or almost 0, okay? So if you do this in the way such that the product of np goes to lambda, or you can just think of it as a constant lambda at first, so you say just np is kept to be lambda, but you increase n and you decrease p. Well, then it's not so hard to show that x distributed binomial NP actually converges in distribution. So the probability law of this x converges to be a Poisson and a variable with lambda. So let's look at a bit of a computation that does this. So let's look at the computation that says what's the probability of x equaling x for this binomial case. So that's going to be n choose x, p to the power x, 1 minus p to the power n minus x. But if we're willing to think that the product of np is lambda, then instead of p, we can write lambda over n, right? That's what we can do. So I'm going to go down here and I'm going to write lambda over n. And for the 1 minus p, put 1 minus lambda over n, all to the power n minus x. Okay. Now, let's actually just take this binomial coefficient and open it up. So I'll write that this thing is equals. I'm just continuing here. And now I keep in mind that I want to do a computation where in the end, I want to get to something which is like the Poisson distribution. And you see in the Poisson distribution, the active part is lambda to the power x divided by x factorial. Let's see if we can already find this lambda to the power x. Well, we do, and an x factorial in there. Yeah, I think we can. So I'm going to write here lambda to the power x divided by x factorial. And then from this bit, what I have is a remainder of n factorial n minus x factorial. And I still have a bit more left here. So I have from this bit lambda so here from this bit I have a 1 minus lambda to the power n still to n minus x, and I still have a 1 on n 1 on n to the power x. Okay, so this was this first reordering that I've done. Now, what I want to do is I want to take this component and just write it in a slightly different way. So I'm going to keep lambda to the power x and x factorial. But now n factorial over n minus x factorial, where that is n times n minus 1 times n minus 2, all the way up to n minus x plus 1. We've seen this type of computation before. So notice that there are x multiplicands here, right? Now, in the same way, for each of those x multiplicands, I can just write an n from this n to the power x times an n times an n times an n. So all of these components here I've written as such. And we still have further. Let's now just break this 1 minus lambda to the power n minus x. Let's write it as 1 minus lambda to the power n and multiply that by 1 minus, sorry, when I say 1 minus lambda, I mean 1 minus lambda over n. 1 minus lambda over n to the power minus x. Okay, so now this was just a massaging of the binomial probability mass function. This is probably not the normal way that you would write the binomial probability mass function. But if you now go to this guy and you do n going to infinity and p going to 0 in such a way that really p is a function of n such that p equals lambda divided by n. Okay. So what you get is the following. Look at this component here. This one does not have an n or a p, so it just goes to be lambda to the power x divided by x factorial. Now, if you look at each one of these ratios, n over n, n minus 1 over n, n minus 2 over n, up to n minus x plus 1 over n, x is a constant that we're not taking to infinity. It's n that we're taking to infinity. So each of these just go to 1, to 1, to 1, to 1. Okay, all of these x elements just converge to 1. Now, a key thing is this thing. So what is limit n to infinity of 1 minus lambda n to the power n? Well, that is nothing but e to the minus lambda. Okay, so you get that by, that is one of the definitions of the exponent. And if you would have had a plus 1, it would have just been e. But since you have a minus lambda there, it's e to the minus lambda. So this guy goes to be e to the minus lambda, which we get right here. And finally, if you look at the last component, 1 minus lambda over n to the power minus x, notice that the power minus x is constant. It's lambda over n, and you're taking n to infinity, so this goes to 0, this stays at 1, and the whole thing just goes to 1. So there we go. We've now achieved the Poisson probability mass function. So that is the probability that y equals x. Okay, and this is how the Poisson distribution can be viewed as a one parameter approximation of the binomial distribution, where you no longer say that you're just looking at n events. You're allowing for a continuum infinite number of events, and you can think of it as that you've taken the unit time and you've split it into many small intervals, and there's a continuum number of events where you're average number of events, well, we even know what the expectation is. The average number of events per the whole time unit is lambda. But you look at the sky and there's not a limited number of shooting stars so you could see. I hope for you that you see as many as possible. And indeed, that's why the support is unbounded. Okay. In general, if you were to plot this probability mass function, it will look something like this, okay? And you would see plots of it elsewhere. So that's what we wanted to say about the Poisson distribution. Now let's speak about another friend of the binomial distribution, the hypergeometric distribution. All right, so if Z is distributed hypergeometric with R and little n and n, let me see that that's how I parameterized it here at the start. No, I put the order different. I'll put n, R, and n. That maybe makes more sense. I'll explain in a sec. Then, first of all, let's say what that means. That means that the probability that Z equals X, and I'm just going to give a formula at first, is going to be, so now it's a formula involving, it looks like a a formula arising from an equal probability space, and it is. And in the denominator, you have capital N choose N, and here you have R choose X, and N minus R choose N minus X. So you got these three binomial coefficients. And this is actually valid for X. Well, we would have liked to say that this is for X. We would have liked to say that this is for X from 0, 1, 2, up to N. But actually, this is not always the X range that we get. It's actually for X equaling from the maximum, and we'll dive into this for a bit, maximum 0, R plus little n plus capital N, up to the minimum of N and R. Okay, so the support of the probability distribution might look a bit weird, all right? But keep in mind that if this number here, R plus N, this is plus N plus capital N, okay? If the minus, sorry, let me fix this. R plus little n minus capital N. Keep in mind that if this number here is negative, then what you get for the bottom value of the support is 0. And if R is greater or equal than N, then what you get for the capital number is N. Okay, so when you're just thinking about hypergeometrics, you might start to think that at first this is a support. Now, of course, you would like to show that for this support, and you can actually look at the kind of the four cases. Is this a lower bound? Is this a lower bound? Is this an upper bound? Is this an upper bound? So you've got different cases of the support, but in each of those cases you can show, and I'll leave it to you as an exercise to show that the sum, first of all, these are non-negative because these are binomial coefficients, and the sum of x on this support of probability of z equaling x is going to be 1. So it's a valid probability mass function. And we won't speak about its mean and its variance today. We'll leave that for a future time. But let's actually speak about the distribution and what it means. So the whole story about a hypergeometric distribution is when you have a population of a total of n items. Okay, so think of them as, say, as apples in a some bucket, and the apples are shuffled uniformly, and there's capital N items of these apples. And what you're doing is you're sampling out little n items. Okay, so little n has to be less than or equal than capital N, and you're pulling out a few little n items. This is your sample size. But when you're pulling them out, you don't put them back. So if you pulled an item, you take it outside. You pull an item, you take it outside. And the items you pull uniformly, or let's say, each item has the same probability of being pulled. Now, the thing is that R of these items are, call them special or good. So R of them you can paint in kind of red. Okay, I'm just erasing them here by accident, sorry. So, whoops. So R of them are red, or called successes, or what you're wanting to count, okay? So there are R, let me paint this in one way or another. There are R of these, which are of the good kind. And that, of course, leaves n minus r of the other kind. Whatever is good or not good, that depends on the context of the problem, but you can call them R successes or R apples of the type that you like or something like that. So this immediately also, I just want to say that you could have also parameterized a hypergeometric distribution in a bit of a different way. Instead of having n and r, you could have had, for example, n1 of one type and n2 of a different type. Okay, but now n is our number, which is the total population size, and it's greater than r, which is the number of special ones. So these two numbers here, they describe kind of the population, how many in total, that's a capital N, and how many good ones. And this parameter here, this number here describes how many you're sampling out. Okay, little n. So now the meaning of the random variable, all the meaning is how many good ones did you sample out? But keep in mind that the story is you're sampling now without replacement. So from a combinatorial perspective, this is a probability that you can just derive. I mean, you can derive this quantity, or you can build this just from combinatorial considerations by considering an equal probable probability space, where your denominator here is the total number of possibilities of choosing a set of, say, size little n out of a set of size n. So that's the total number of sets that you could have chosen. And to get the event that you had X of them that you chosen, so now you've got your little sample, right? And you've got maybe little n was say 5. So you've chosen 5. And to say that, say, two of them are are good, so you've got two red ones, then you'd say 2 equals here. So how many possibilities out of 5 do you have 2 good? Well, we'd need to choose from the R good ones. What are those 2 that we chose? And then from the remainder, from the not good ones, the capital N minus R, remember this is a parameter that can also be N2 if you'd like. Okay, and then this one would have been N1. Okay, and this one would have been N1 plus N2. All right, if you do that parameterization. So from that number, we need that n minus x, this would be our 3 bad ones. This would be the 3 that you don't choose. So this numerator counts the number of elements in the set that says that it's the number of elements in the set that counts, that says how many outcomes do you have of a sample from these capital N apples or capital N whatever that have X being good and the remainder N minus X being bad, right? So the bad ones you have to choose from a subset of the bads. Okay, I hope I described that okay. But then, how is this? First of all, there's a few questions that we still need to do. So how do we get this kind of support? Why is this a support? That's one thing. And the other question is, what is a relationship to a binomial? Okay, so we saw how Poisson is related to binomial. How is a hypergeometric related to binomial? Okay, so let's just understand the support a bit more. So we're saying again, I'll just write it here a bit more clearly. So x can be anywhere from its smallest value, which is actually given by this maximum, and that's the maximum of 0 and n plus r minus capital N. Right? Is this how I wrote it here? N plus R, yeah, R plus N minus capital N. That's okay. All right. And, whatever this number is the smallest possible value. And then you can have the next one. So if you can call that X min, for example, and the next one will be X min plus 1, and then X min plus 2, up to the last one, which is going to be the minimum of N and R, and that's X max. Okay, now again, you might end up with a situation where X min is actually 0 and X max is actually little n. And that's the most kind of easy to digest situation, because then when you're pulling out n apples here, say if you chose 5 apples, you can have 0, 1, 2, 3, 4, or 5 good apples, right? But in what kind of situation would this X max be given? Maybe this is very unclear. This is an N, and this is an R. In what kind of situation would it be given by R? Well, look, if in our population, for example, so say, let's choose capital N to be 7, but we only have in our population 1, 2, 3, 4, 5, 6 apples, then of course we're not going to be able to sample 7 apples because we're sampling without replacement. So then X max is going to be given by R. Okay, so if R happens to be less than N, then your maximal number of successes is given by that. Now, the other case, again, X min might be 0. It might be a situation that we actually choose 0 samples out. But what if, say, what if N here was very small? Sorry, I actually mean, what if N was like a large number, say 10, in comparison to the number of failures or the number of bad elements in the population? Let me put X's on the bad elements in this population. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. You know what? Let's just to make it a bit more clean, let's make N to be 11. Okay. So say we're now sampling 11 elements out of this population, and we've only got 9 um, bad ones. Okay. So in this case, are we going to be able to attain this situation of 0, of getting 0 successes? Well, you could say it has to do with how many good elements we have, right? So, I mean, if we had many good elements, you might think, well, yeah, we will be able to attain 0 successes. But no, 0 successes means that your whole sample here, your whole sample of 11 was given by bad samples, and you can only get 9 of them. So the smallest number you can get is that you got all of the 9 bad samples, and that is 11 minus 9, that's 2. So if you look at this expression here, at this one here, you can write it as n minus n minus r, right? So this is number of bad elements in the population. And if this number is greater, if this thing is greater than 0, that means that n is greater than n minus r, and that's when this lower x min would be attained by this boundary. And that's because you have to sample some bad items. But in general, I want to say again, if n is less than, if you say, if you're looking at the parameterization that calls the parameters n1 and n2, right? The number of samples that are the number of elements in the population that are good and the number of elements in population that are bad, then if little n is both less than n1 and n2, then all values are possible. So that's what I wanted to say about the support of the hypergeometric. Sometimes it's a bit confusing, but there's not much more to it than just knowing that because we have 3 parameters, little n, r, and capital N, we can get a few different situations. Now, finally, I want us to go back to this apple sampling situation where we have some, let's call them good apples, and we have some bad apples. Okay. And we're pulling out n of them. If we were pulling out n each time looking at the apple and then tossing it back, well, that is sampling with replacement. And in this case, the probability distribution of the number of good apples would just be a binomial distribution with n, and with probability of success, it has to do with proportion, the proportion of number of good apples to bad apples, say R over n, or n1 over n1 plus n2 if you were to parameterize it differently. The whole thing with a hypergeometric distribution is that every time we pull an apple out, it's out, okay? And that's it. It changes the sample. So you no longer maintain kind of a situation of IID sampling. Okay. So what you have out here has now changed what you have inside. However, well, think about N1 plus N2 or capital N and the population size growing. Say you now had like 100,000 apples here and you're sampling 20. Does it matter if you put them back in every time you sample them or not? No, not really. And this is where the relationship between the hypergeometric and the binomial kicks in. So when capital N grows to infinity and R, the proportion of apples, grows in a way such that R over N goes to P, well, guess what? You get a convergence that the hypergeometric converges to a binomial. And this will be in assignment 2 of the homework to actually work on it. It's a computation of a similar nature to this binomial convergence to a Poisson. Okay, so we've seen that binomial, if you do some change of parameters, goes to Poisson, and hypergeometric, if you do a change of parameters and limiting regimes, goes to binomial. That's it. These were the two distributions that we can call friends of binomial, and through that, I guess they're also friends of each other. All right, enjoy your day.